we can actually smooth a signal using some kind of filtering. Okay, and smoothing, we have seen like box filter, we have seen Gaussian filter. All those filters help you in smoothing your signal. And when you smooth your signal, what it does is it tries to utilize the neighborhood values and then use the average and replace the value of the current pixel, right, in your image. And it will do the same for the signals as well. So if you smooth, let's say in this case, we are using a Gaussian filter. A Gaussian filter will look something like this, which means that you are paying more attention to the current pixel, slightly less attention to the neighboring pixels, but you're still looking at the neighborhood. So it will have some kind of smoothing effect. And if you perform filtering using this Gaussian kernel of this function, then this is the filtering operation. And you can see that the signal becomes something like this. So all the noise is actually gone. So filtering using Gaussian is helping you in getting rid of the noise which was there. And then what you can do is you can just compute derivative of this filtered signal. Right. So if you compute derivative, it will give you something like this. And this bump over here actually corresponds to this change in signal intensity, which represents an edge. Okay, so smoothing is like one operation which helps you to address noise and still be able to compute edges in your signal or in your images. Now, there is like some optimization which you can perform here, and we'll talk about optimization a lot when we talk about filtering or edge detection later on. So if you look at this operation, right? So this is a filtering, or you can say correlation operation, right? And you're computing derivative of this function, and we have seen that if you compute derivative, it's kind of you can compute derivative of the filter itself, right? And then apply that to the filter. So this was the original filtering operation, and you are computing the derivative, right? So you can bring out like the function itself and just find the derivative of a kernel. Okay, because convolution is differentiable. We, I think, saw that in one of the properties in the last lecture. Now, why this is important? Because your function or your signal or your image, that is going to change, but you beforehand know what your filter is going to be. And if you know that, you can compute the derivative beforehand. Okay, you don't have to wait for the signal itself. So for example, if our filter was Gaussian, then what we can do is we can just compute the derivative of the Gaussian, and that derivative is not going to change at all. And what we can do is then use that derivative of Gaussian to actually perform filtering. All right. So if you compute derivative of your Gaussian, you will get something like this. And I can go over this quickly, but I don't think there's a lot to understand here. So your Gaussian will look something like this, right? So when you're computing the derivative, again, you can see that your signal value is actually increasing. Again, we can just follow the slope. Initially, the slope is 0, and it's gradually increasing. And the slope will be maximum when you are at this location. Right, so that corresponds to this value. But again, the slope is going to come down. And as you reach the top, the peak over here, again, your slope is 0, which corresponds to this location. And again, you can repeat the same thing for the other half of the Gaussian, but again, it's in the different direction. So you get like a peak towards the negative direction, right? So that's the differentiation of a Gaussian function. And now what you can do is use this kernel to perform filtering, and the result is not going to change. You will get exactly what you got using like these 3 steps. Okay, so you're saving like 1 step here. So that's kind of optimization. All right, so we discussed like smoothing helps, but again, it's really important to understand. We also saw that in the last lecture, it actually depends what kind of filter you're using and like what's the size of your filter, and that will completely change the kind of output you're getting. So you can just have like, you can just use 1 pixel, which means you're not changing anything. You can use, let's say, smoothing over 3 pixels. It could be a 3x3 kernel. Then you will see that the edges are actually also getting blurred. And if you keep increasing the size of the kernel, it's going to be even blurring. Okay, so which means that if you do too much smoothing, I mean, of course, it will remove the noise, but again, you're losing on some of the edges as well. So if you will have like very soft edges, all those edges might be gone just using smoothing. So if you want to recover those edges, then smoothing might not be a good idea. Okay.